So next up we have Joris Ceulemans. He's going to talk about the Sikkel library or multimodal simple type theory.
Yeah, so hello everyone. My talk will be about this Sikkel library that can be used to, that can allow you to use Multimode simple type theory as an Agda library. Now, some of you may have seen a talk by me about this, so I'll also, at the end and throughout the talk, give an update on work in progress on how you can also use it to do not so simple type theory. So why do we actually want to do this? So our dependency type languages like Agda are based on a theoretical framework like Multimode type theory. And over the past years, there has been a lot of research that extends these theoretical type theories with new primitives. And those new primitives allow you to write more programs or prove more properties, which is basically the same, of course. So you can think, for instance, of systems with guard conversion, parametricity, univalence, that kind of stuff. And the question is like, well, most of these systems have been designed as theoretical systems, and we actually want to benefit from these new primitives when we're programming in Agda. And so how can we actually do that? And so the approach we took is like, unlike what most of us are doing here at the meeting, is we decided not to start hacking Agda, but see how far we can get by implementing this as an Agda library within Agda. So this is a very broad overview of our library. So as you can see, it consists of 3 layers. And all of these are implemented in Agda. And so the first is a syntactic layer. It provides a formalization of what we call multimode simple type theory. And at this layer, you can write your programs, and those programs can make use of the new primitives that you want, that your extended type theory presents you. And then at the second layer, we have a semantic layer. So that consists of a formalization of pre-sheaf models of type theory. So that's a rather very broad class of models of type theory. So we formalize that in Agda. And so there is an interpretation from programs at the syntactic layer that computes their denotation at this semantic layer. Now the question you could ask is, why do we need that? And that's basically because this formalization of the syntactic layer is basically just a data type of abstract syntax trees. So if you write your program, what you get is a value of some inductive data type, and so not really an Agda function that you can use to compute values. So now you can compute the denotation of this program at the semantic layer, and then this denotation of some programs can be extracted to the third layer, the meta level, which is Agda, which is the language in which all of this is implemented. So the denotation of some programs can be extracted to actual Agda functions that you can use to, and that you can import and use in for instance, other Agda developments as well. But I'll say more about this further in the talk. So let's first take a look at this syntactic layer, at this multimode simple type theory. So actually, it's the multimodal type theory by Daniel Gratzer and co-authors, but restricted to simple types. So what this means, well, just like MDT, MSCT is parameterized by a mode theory, and such a mode theory is basically a strict small 2 category. And in that 2 category, all the objects are called modes, and all the 1 cells are called modalities. And so we'll not bother with the 2 cells today. And what you should think of is like, at every mode, there is a copy of Martin-Löf type theory, or in the simply type setting of, let's say, simply type lambda copies. So at every mode, you have functions, you have products, you have natural numbers, booleans, etc. And the modalities will provide new primitive constructors that will allow you to transport definitions at one mode to another mode. So how does that work more concretely? For every modality new from a mode M to a mode N, you get a new primitive operation of context, the log operation, and that will transform a context gamma at node N to a context gamma log mu at node M. And you also get a new primitive type operation to produce modal types. So it will transform a type t at mode n to a type nu t at mode n. And you can kind of think of these, well, kind of adjoints, but they'll be a little bit more clear on the next slide. So how can we actually program in this system? So let's just look at an example. Suppose we have this mode theory with 3 modes and 2 modalities, and we want to construct a function of this type. So what I should mention is that this circle M is a composition of modalities. So since modalities are just one cells in a category, you can compose those. And so, well, a function of this type could, with some imagination, might express that this kappa modality is an applicative functor for restricted to modal functions of type mu a to b. So, what do? We have an empty context. We want to construct a function of this type. It's a modal function with modality kappa. So we use modal function abstraction. And that has the effect that we get a variable in our context. And as you can see, every variable appears here in the context under a certain modality, in this case modality kappa, because we use lambda abstraction with modality kappa. And then we still need to produce a modal function, this time with modality kappa composed with mu, so we do the same thing again, and we extend our context. And now our goal becomes the modal type kappa b, and we can construct a value of that using the modal constructor for terms, which is called mod kappa. And this has the effect that we can construct a value of type kappa b by constructing a term of type b, but after locking the context with this type kappa. So this is part of the adjunction that I told about. Okay, so all we're left with is constructing a value of type b. And so basically what we want to do is apply this function f to the argument a. But we cannot do that directly because f is a modal function, so we use modal function application, and that has the effect that the argument of the application will be checked in a context blocked by the modality mu. And so now these two holes should be pretty obvious to fill. So here we use the variable f. There is only one side condition that should be satisfied, and it is you can only use a variable in this system when the modality under which it appears is equal to the modality of all the locks to the right of it, to the composition of all these locks. So here, f appears under modality kappa. There is only one lock to the right of f, which is also modality kappa. And so that means that we can use this variable at this position.
So can you go back one step?
Yes.
See the context.
Okay.
Oh yeah, right. Okay, yes.
Okay?
Yes, I'm happy. Yeah.
Right. And so in the remaining hole, we do the same for the variable a. It appears under modality kappa composed with mu, but that's also exactly the composition of the blocks to the right of this variable a. So I'll let you stare at it for a few seconds. And that finishes our program. Right. So that's how you program in this multimode type theory. How do we formalize that in Agda? For types and contexts, it was pretty obvious what to do. They are inductive data types indexed by the mode they live in. For terms, there is this two different types of presentation that Phil also talked about on Friday. So you could go for an extrinsically typed representation in which the type of terms is also just indexed by a mode, and then, for instance, this modal type constructor would have a type, well, it takes a modality from M to M and produces a term type in mode M from a term in mode N. But you could also go for an intrinsically typed representation where you basically encode the entire typing rule in the data type of terms, and where you index them by the context and the type. So there you would actually encode the typing rule that for a modality mu, you have to provide a term of type t in context gamma of mu, and you get a term in context gamma of type mu t. Now, there are like a couple of advantages and disadvantages specific to modal type theory, which made us choose the extrinsically typed variant in the first release of our library. And what are these? Well, basically, also as the discussion on Friday had some of a conclusion, it was like intrinsic typing is difficult if there is non-trivial type equivalence. And that appears here because you have modalities in your type, and modalities might have non-trivial equivalences. Like you might have mode theories where you have like non-trivial equivalences between modalities, which gives you non-trivial equivalences between types. And so if you want an intrinsically typed approach, you actually have to come up with some canonical representation for each modality. And in an extrinsically typed version, that is not needed. And also in an extrinsically typed setting, you can do mode and modality polymorphism in an easier way, because you don't directly encode the typing rules. Now, of course, in the extrinsically typed version, in the overview, there was an error from the syntactic layer to the semantic layer. That will, of course, also include type checking. So not only interpretation, but also type checking, because you cannot interpret programs that are not typed. There are, however, some advantages of intrinsically typed representation. That is, for instance, that you get support from Agda when programming, like what I showed here in the example. The context and the expected type are always visible. That's not the case anymore when you have an extrinsically typed version. And like it might be obvious to state, but it will become important further on in the talk. The interpretation in the model is, in this case, a total function, and there is no type checking involved here. Right, so enough about the syntactic layer. Let's see what the other layers are. So I'm going to explain that using an example of guarded recursion. So here you can see a mode theory for guarded recursion. This system is completely implemented in the Sikkel library. So we have two modes, star and omega, and a couple of modalities. And here you also have, for instance, non-trivial modality equivalences. For instance, later composed with forever is actually just forever, that kind of stuff. Now, at the semantic layer, closed types will be interpreted as capricious. That means they will be interpreted as diagrams of Agda types and Agda functions. And so the shape of those diagrams will depend on the mode where the type lives in. So all closed types at mode star will be interpreted as just an Agda type represented by this box. However, closed types at mode omega will be interpreted as a sequence of Agda types with functions going from n+1 to n for any n. And so, and terms at these modes will be interpreted as terms of the Agda types, well, of all of the Agda types that fit with these functions, but that's not too important for now. The fact that we can interpret these types as diagrams allows us to provide meaning to all of these modalities here. So for instance, the later modality here will be a transformation that transforms one diagram into another diagram of the same shape by just shifting everything one step to the right and adding a unit type in the front. Or for instance, this constantly modality will just take an Agda type here and produce a constant sequence here. And so the fact that we interpret these types as diagrams makes it possible to actually implement what all of these modalities should do. And so that's how this appreciative semantics works. And as you can see, types at mode star are basically just interpreted as just an Agda type, which makes it very easy to extract types and terms at this level to an ordinary Agda type or an ordinary Agda program. There is something going on here because like this type is not always the exact type that you want, but that's a detail that I won't go into now. But what you can see is like there is this extraction mechanism that is pretty elegant. So you can, one thing I forgot to mention is that, of course, you can also extend Sikkel with other primitives than the modal primitives. For instance, you could also extend it here at the mode omega with some guarded fixed point operation. And then you can write some functions using this guarded fixed point operation, transport them with this wrapper modality to mode star, and then extracting to Agda to get actually Agda functions or Agda streams that compute and that were defined using guarded recursion. So I think I said a lot of the content of this slide. So what are the advantages of using Sikkel? Well, it's completely general in the mode theory or in the base category of the pre-sheaf model. There is this elegant extraction mechanism that makes use of the different modes and modalities. And it also allows you to make some kind of modular use of type theory extensions. So, for instance, if you're in an Agda development and at some point you realize that you need guarded recursion, you can just instantiate Sikkel with the mode theory for guarded recursion, write your program, extract it to an Agda function, and if at some other point you realize that you need parametricity, you instantiate Sikkel with the mode theory for parametricity, do your stuff, and also extract it to ordinary Agda, and you can keep developing the other parts in standard Agda without bothering with the modal stuff. Now, of course, if you want to combine these two, you'd have to think about how to combine the mode theories for guarded recursion and parametricity. There are also some disadvantages, like for instance, the syntactic layer uses some customly defined syntax, so you cannot use interesting Agda features, and it's restricted to this MTT style of modal system, so there is no substructurality, there is no, for instance, quantitative type theory that you can do with the system at this moment. Right, so that's basically a summary of the first release of the Sikkel library. Now, what's the next step? Well, as I told you, Sikkel is currently simply typed, so you can only write simply typed programs. What we actually want to do is to reason about this program and also reason about the extracted Agda programs that we obtain, prove properties of those. So what would be the logical step to do next? That is extend the syntactic layer of Sikkel to dependent types. And I've tried that, and I've tried several approaches. For instance, the intrinsically typed approach, using, for example, the quotient inductive types. But in my opinion, that makes it very hard to actually write programs. It's very, very useful to study the meta theory of dependently typed programs, but because every definitional equality in your theory becomes a propositional equality, you'll have to provide witness for all the definitional equalities in your theory, and that becomes very hard and very cumbersome when you actually try to write programs using that approach. You could also go for the extrinsically typed approach, but there I run into issues with the termination checker when trying to implement a type checker. So the current approach that we're taking is postpone the dependent types for the moment and add a dedicated layer just for proofs. So the overview would look something like this. So this is what I showed on the first slide, and we're actually now adding this part. So there is now a logical framework that allows you to reason about these MSTT programs. And what I should also mention is that these pre-sheaf models already support dependent types. So what we hope to do is to provide a proof of soundness of this logical framework in this pre-sheaf model. And the idea is then that you could also extract these proofs to obtain Agda proofs of your extracted Agda programs. And in this case, it becomes really important why your interpretation function here is a total function. Because if here you're doing type checking and you have a partial function, then even stating this soundness condition becomes very, very hard. Because, yeah, I mean, soundness would also intervene with type checking, and that would become an intricate thing to do. So again, here is the first attempt. We defined some type of propositions or formulas, as I call them. For instance, equality of two terms of the same type. So here, notice that I'm working with this intrinsically typed approach, just for the reason that we have this total interpretation function. We have a junction and a bunch of other connectors for constructors for formulas. Among others, there are some modal constructors here. And then we could define an intrinsically typed proof system in which we just encode all the judgments, all the different derivation rules as constructors. So for instance, here we would get an introduction rule for conjunction. Note here that this proof context is a context that contains ordinary variables and also assumptions. And so this true context here is a function that just drops all the assumptions, all the propositions, and only keeps the variables. And this works in a non-modal setting, so I first tried to do this without all the modal stuff, and that worked fine. But as soon as I extended this to a modal type theory, then it became very, very, very slow to type check these proofs. So for instance, I tried to prove in this system that addition is commutative, and that wouldn't be type check. So there were no modalities involved, but it was in the modal system, so the syntax had modalities. I write a non-modal program in the system, like addition, and I tried to prove that addition is commutative, and it wouldn't type check. I've been took a lot of time to figure out what the problem was. I have some idea of what's going on. So I think that in your modal type theory, substitution is quite an intricate thing to implement. And so the terms that you get after substitution can get quite big if they're not reduced to normal format. I mean, the Agda terms representing the syntax that you get after substitution can get quite big if they're not normalized immediately. And I think that like a potential cause of the performance issues here is that Agda is not eager enough to normalize all of these operations, normalize these indices here in the inference rules, so that you get very, very big Agda terms. So that's my suggestion of why it might be slow. In any case, this is very slow to type check. So how I try to solve that now is by going to extrinsically typed proofs. So we just say here, like this is a proof in this context. I'm not saying what it exactly proves, and then I'm writing a proof checking function that takes the proofs, takes a formula, and checks if this is a valid proof of that formula, and gives back the result. Of course, it has, again, some downsides. For instance, we don't, when constructing a proof, we don't immediately get the proof state, so we don't, at any point, we don't get what's the goal that we still have to prove, and what are the assumptions that are currently in our context. But that's currently solved by allowing custom goals in this proof syntax and extending the check proof function so that it also can give you some kind of that information and then partially check the proof. What's still work in progress is making the checker support beta equivalents and not only alpha equivalents, providing a soundness proof for the modal system, and expand the set of inference rules, so that is currently quite limited. Other things that are like future work, but for less near future, are looking at the Hoffman-Streifel universe at the semantic layer, extending the syntax to full dependent types, still thinking about how that actually can be possible. There are currently also no inductive types at either the semantic or the syntactic layer, which could also be very useful, and considering other applications. So we already have hardware version and a very restricted form of parametricity, and some preliminary exploration of normal types. So that's everything I have to say. Thank you.
So Agda has a primitive called force in Agda.builtin.strict.
Yeah.
Have you tried using that? I mean, it reduces only to weekend normal form, so
yeah.
maybe it's not enough.
So I tried using that, and then I had to force a lot of things, and that didn't actually improve the situation
okay.
a lot. But that might also be due to the fact that I didn't use it properly. I mean, that some things got reduced to weekend normal form and not to...
Right. I don't think it's something that a lot of people use or even know about, so it's definitely possible that it's just not properly implemented or not doing the right thing for this situation. But, but it would be interesting, if you can have some better ways to support strictness in Agda. It seems like a reasonable, and especially strictness during type checking.
Maybe we can have a strictness modality.
Yeah.
Go ahead.
It's really nice, I think, that you started hacking, or not hacking Agda, but instead use Agda itself to have a new variation on type theory. And I might also provide a case in point that having some Agda core language can be really beneficial. Like you said, how you could compile different variants of type theory to Agda in your framework. And this is more of a remark to the community that this might be actually a quite nice approach to kind of decouple the different variations of cubicle Agda and all these, and really kind of make all interoperable with some core language, which you kind of did in your framework, but at some point you, I guess, reach a point where type checking is difficult.
Yeah, so I think one consideration there is also performance. If you try, I mean, there are people who try to formalize cubical type theory in type theory, and that is theoretically possible, but I don't think that's the approach to take. Or I don't really have a very strong opinion on whether that's the approach to take, but you should try to, people should try it and then see how, for instance, performance is going, and see if that's actually a useful approach. So I don't know whether that's the way, but it might be an approach to explore.
You mentioned that the type theory is parameterized by a bicategory of modes, and the modalities are the one cells, but where do the two cells come in?
So I said I wouldn't bother with those today. So actually...
No, I'm making you.
Yeah, that's very good. So actually, I lied a bit, because I said here, you can use this variable f only when the modality is equal to the composition of all logs.
Right.
That's a lie. Actually, what the condition is, there should be a 2 cell from this modality to the composition of all logs. So these 2 cells control which variables you can use as a term.
And this is reflected in the formalization as well?
Yeah. But I wanted to keep things during the talk.
Release the mic.
Yes.
So you mentioned free-shift models, so I guess you need, for each mode theory, you need a somewhat custom free-shift model, or is there a general notion which you can instantiate?
Yeah, there is a general notion, so that is also parameterized by a base category, and basically every mode corresponds to a base category. So there is a translation from modes to base categories, and then types at a certain mode are interpreted as free sheaves over the base category corresponding to that.
All right. And then the 2 cells are.
The 2 cells are so the modalities are interpreted as dependent right adjunctions between the different free sheaf categories, and so that gives you functor between context categories, and then the two cells are natural transformations between these context functors.
That makes sense.
One more question. So you mentioned, yeah, you have to write your programs down in this syntax, which doesn't have support for things like meta variables or like other things that we expect from Agda. Right. So at one of the previous Agda meetings, we discussed having a kind of a reflection API for abstract syntax instead of internal syntax. So you could kind of, so because currently all the syntax that you write has to be first type checked and then you can reflect it and do things with it. But having some way to get it before it's type checked even and do your own custom elaboration for the syntax.
Would that help?
Would that help in this case? Would that be a thing?
I need this. I've had the need for this.
Right.
Maybe I need to think about it.
Right.
What is?
I mean, so then it would require quite a bit more work because basically you're implementing your own elaborator then.
Yeah.
So the question is like, I mean, that was also the question we got kind of stuck on back then was, well, how much desugaring do you want to do before you hand it to this abstract syntax? And it's not obvious. Like, yeah, probably for each application is going to be a different point. So yeah, not obvious what to do exactly there.
Yep.
But this, I thought maybe this might be a nice use case for that.
Yeah, maybe.
Just if you're abstract syntax, what part of pipeline has been done?
Scope checking has been done.
Operator parsing?
Operating parsing has been done.
We would probably
And
also
like things like do notation
let
and
variable names.
yeah. But we haven't, for example, we haven't inserted implicit arguments yet. So that maybe that's something you might, well, yeah, so I don't know.
Basically, that would allow you to define any language.
Yeah.
Yeah,
I thought that. Yeah.
but just using the Agda parser and scope checking.
But then you need to also be able to specify modalities, user-defined modalities for this.
Yeah, yes. Well, we have the add annotations already.
Yeah, but that would need to be specified in the Agda file.
Yes, so yeah, so it would not be, I mean, it would be a big project to make it work for this application.
Do you think that we can take insight from Sikkel and from Gratzer's multimodal type theory to like clean up Agda's handling of modalities? You mentioned that it's not usable for substructural modalities.
Yeah. So I mean, like the past days we've been working with this modality structure, and I think it's fair to summarize it like currently it's quite a mess. So,
yes.
Yeah, I think you can get quite some insight from these modal type theories to do that more structural. Yeah, but I think that's also too big of a project to finish in these
one
two remaining days. So.
That's the problem by things. I mean, things that don't fit into one Agda meeting, they just don't get done.
Yeah.
After 1 year.
2-week meeting.
Have a special year on Agda.
Yeah, it would be nice if you could like declare your own modes, modalities, and two selves in Agda and have that be handled for you.
Yeah.
I mean, that's kind of the opposite of what you've done. I think it would be nice.
Sorry, I didn't.
If you could like postulate or declare in some way your own modalities, your own modes, modalities, and two selves.
In this extension,
Yeah.
Yeah.
In a hypothetical multimodal Agda, essentially.
That would
then
be
we
very
could get rid
nice.
of flat, right? That wouldn't have to be implemented in the type checking.
That would be very nice, but yeah.
And probably get rid of blocks.
Getting even further in the direction of build your own Agda.
Build your own Agda.
Stop that though, right?
Yeah.
You made something bad.
I mean, well, it's. I think already for like. From a newcomer point of view, this is, we at least should like provide sensible defaults and like avoid overwhelming them with too many choices. And I think currently that's already a big problem or like a big bottleneck with the adoption of Agda, is that you have to just do a lot of, make a lot of choices and do a lot of things. It's very much not batteries included.
Maybe to vaguely answer your earlier question, if you're people doing something similar in Cork who have actually a translation from Cork to their syntax. So not from Cork abstract syntax, really from Cork.
Yeah, but I mean, that you can already do in theory with the reflection API we have.
Yeah. But then I guess for this application, the main thing you need is custom multimodal applications.
Right. I mean, that's also kind of what we did with using reflection API to build extractors. Only in this case, you would build an extractor back into your theory, which is also defined in Agda, right? So you first parse the thing as some weakly typed thing, and then reflect the term, and then retype check that with your own custom type checker. That would be another way to do. With the current architecture of Agda already kind of reuse the Agda syntax, but yeah. I don't know. It's a practical thing. Any more questions? Otherwise, let's thank Joris and go to coffee.